So some more examples of using implicit differentiation. So here I have 2y equals x squared plus sine of y. This actually is a function, but this is an example of it's really nearly impossible for us to isolate the y within a reasonable amount of time. But with implicit differentiation, I don't have to. So again, I'm noting x is my independent variable, so anything that's not x is going to require the chain rule on it. So the derivative of 2y is 2, but that's not an x, so I need dy dx. Equal sign, derivative of x squared is 2x, don't need chain rule, plus derivative of sine of y would be the cosine of y, but y isn't an x, so I need to do times dy dx. But now I need to isolate dy dx because I'm specifically told to find dy dx. So to do this, I'm going to subtract cosine y dy dx from each side. So I have 2 dy dx minus the cosine of y times dy dx equals 2x. I can now factor dy dx out of the left side. And now I can divide both sides by 2 minus cosine of y. And I get that dy dx is equal to 2x divided by 2 minus cosine of y. And there is our derivative. I really like this topic. It makes these so much easier for us. So then, if I wanted to find the equation of a line tangent to the ellipse at the point -1, 2, I have my ellipse. So equation of a line tangent, that means the shape is a line. We use point-slope form, so I need to know the point and the slope. Fortunately, they tell us the point. I just need to figure out the slope. Well, another name for slope of the tangent is the derivative. So that means I need to find dy dx. And an ellipse is not a function, so I'm noting x is my independent variable. So anything that is not x, I need to do the chain rule on. So the derivative of x squared is 2x. Don't need chain rule. Minus x times y is going to require the product rule. So in parentheses, I'm going to do my product rule. First times derivative of y, which would be 1, but then I need the chain rule, dy dx, plus y times the derivative of x, which is just 1. And then I have my plus sign. Derivative of y squared would be 2y, but that's not an x, so I need a dy dx. Then my equal sign, derivative of 7, that's derivative of constant, which is always 0. But I need to isolate my dy dx, so I'm going to distribute my subtraction to get rid of my parentheses. So 2x minus x dy dx minus y plus, not equals, plus 2y dy dx is equal to 0. I'm going to move the 2x and the minus y to the other side of the equation. So negative x dy dx plus 2y dy dx is equal to y minus 2x. Pull the dy dx out on the left-hand side of the equation. And then I can go ahead and divide to get dy dx by itself. And then that's not where I'm going to stop, because the whole idea of me doing this was so I could find the slope at the point -1, 2. So I need to know what's dy dx such that we're at the point -1, 2. Plug those in for x and y. So 2 minus 2 times -1, which would be a plus 2, over 1 plus 4. So this is 4/5. And now from the point and from my slope, I can write my equation of the tangent, which would be y minus 2 is equal to 4/5 parentheses x plus 1. And here is the equation of my tangent.